However, if outlook is equals to sunny, we can see the reduced data set here. We do not actually reach a leaf node or a specific decision, as we had seen for if outlook was equals to overcast. So for outlook equals sunny, we see that there is a mixture of decision, some no's and some yeses. So what we'll have to do is again split on another of the three attributes remaining, temperature, humidity, or wind, and check and calculate the information gain of decision with respect to temperature, humidity, and wind, and check which has the highest value, and then choose that attribute to split on. So let's see the calculation for information gain due to temperature, due to the attribute temperature, given that outlook is equals to sunny. So we prepare here a reduced data set again, where outlook is equals to sunny. So we work with only examples where outlook is equals to sunny now, right? And again, we have to actually measure the reduction in impurity or entropy in order to calculate the gain, right? So here, first of all, we calculate the entropy of decision given that outlook is equals to sunny. So we see that there are two values for decision, no and yes, and there are 3 no's out of 5 and 2 yeses out of 5. So pi for the no will be 3 by 5 and pi for yes will be 2 by 5. So we plug that in and we can easily get the entropy for decision given that outlook is equal to sunny. From that, we have to actually subtract the expected entropy of temperature given that outlook is equal to sunny, and this is exactly what we calculate in these parts. We can see from the data set that temperature has 3 values: hot, mild, and cool. So we'll have to average out 3 entropies, right? So for the in the first place, you can see that we have calculated the entropy for temperature equals to hot and multiplied that with the probability for hot. So we can see that there are only 2 values for hot, so the probability will be 2 out of 2 by 5, and we multiplied that with the entropy for temperature equals to hot given that outlook is equals to sunny. We can see that when temperature is equals to hot, then there are only no values, and there are 2 no values and 0 yes values. So pi for no will be 2 by 2 and pi for yes will be 0 by 2. So we plug those in and we can get the entropy for temperature equals to hot. Then we again subtract the weighted entropy of temperature equals to mild, right? So we can see here that we have 2 mild values out of 5. So the probability of temperature equals to mild will be again 2 by 5, and the entropy, and for the entropy we'll have to check how many yes and no values there are, right? So we can see that for mild there is a no and there is 1 yes. So the pi's will be 1 out of 2 because there are 2 mild values, right? So again, using the entropy value, we find out the entropy for temperature being mild given that outlook is equals to sunny. And lastly, we calculate the weighted entropy for temperature equals to cool, right? Since there are only 1 cool value, probability will be 1 out of 5 multiplied by the entropy, and since there is only 1 yes value, the pi will be 1 out of 1 for yes and 0 by 1 for no. By plugging in all the values, we can easily calculate that information gain for temperature, given that outlook equals sunny, will be 0.571. Similarly, we can calculate the information gain for the rest of the features or attributes, given that outlook is equal to sunny. So here we can see the values, and by comparing them, we see that humidity actually has the highest information gain, which is 0.970. So what we should do is, if outlook is equals to sunny, we should in the next level split our decision tree according to the humidity attribute. Right? Upon doing that, we observe another thing, that whenever outlook is equals to sunny and humidity is equals to high, the decision is no, always, for all the examples. So we can we here reach another leaf node. Moreover, when outlook is equals to sunny and humidity is equals to normal, we see that all the decisions for all the decisions for all the examples are yes. So we again reach a leaf node here. So we reflect our findings in the decision tree here. At first, till now, we have split our decision tree according to outlook in the root node, and we had found out that whenever outlook was equals to overcast, our decision to place tennis was yes. But if outlook was equals to sunny, we would have to look into humidity, the humidity levels. If the humidity level was high, then the decision was not to play tennis. But if the humidity level was normal, then we decided that we can play tennis. Next up, we'll have to decide what to do if outlook is equals to rain. Upon observing the reduced data set, we see that whenever outlook is equals to rain, the decisions are mixed. That means we have not been able to reach a leaf node. There is a mixture of yes and no decisions, right? So again, we'll have to split on different attributes, either temperature or humidity or wind. And in order to do that, we'll have to find the information gain for each of the attributes, given that outlook is equals to rain. We can do that easily by following the steps in the previous example that we saw. And upon doing that, we find out that when outlook is equals to rain, the wind attribute actually gives the most information gain. So what we do is split our decision tree according to wind whenever outlook is equals to rain. Upon doing that, we again observe that whenever outlook is equals to rain and wind is equals to weak, the decision is always yes for the example. On the other hand, when outlook is equals to rain and wind is equals to strong, the decision is always no. So we can reflect this directly in our decision tree. That means we have reached a leaf node and do not have to split our decision tree further, right? So if we do that, we can see that whenever outlook is equals to rain and wind is equals to strong, the decision to play tennis is no. And when the wind is weak, our decision to play tennis is yes. So we have our final decision tree because we have reached the leaf nodes for each of the branches. And note that the algorithm that we use to build this decision tree is very similar to the ID3 algorithm, because the ID3 algorithm also uses the maximum information gain method in order to distinguish between which attributes to split upon first. Lastly, I would like to show you guys a general decision tree learning algorithm. So as you can see, the function takes in three inputs: the examples in the training set, the attributes, and a default tree that you might want to return if the training set is empty. So this is like a base case. So if there are no examples in the training set, you return the default tree. Else if all the examples have the same classification, then return the classification. That means that we have reached the leaf node, right? So for example, after splitting in this tree, after splitting with outlook, and in the next level, after splitting with humidity, the examples that were left here all had the same decision, right? For example, just for example, three of the 14 examples in our training set uh, had the decision of no when split with outlook and humidity. So all of these will have the same no decision, right? So we just return that. Else if attributes is empty, then return the mode of the examples. For example, if we hadn't reached a case where all the examples were of the same decision yet, like after splitting with outlook and humidity, then we would have to split here again, right? Maybe with temperature. So let's say we split here with temperature, and still we did not reach a final decision. Then we would have to split here again with wind, right? If a case arises that still after splitting with all the attributes, we do not reach a leaf node, that is all the examples in all the remaining examples do not have the same classification, then what we do is just return the majority of the classification. That is, if there are two yes examples and one no example, then we return yes for this specific branch. Okay. However, if none of the above happens, which is typically the case, then we go and find out the best attribute uh, by calculating the information gain for the ID3 algorithm. So we choose the best attribute in this step, and using that best attribute as the root node, we form a tree. So for example, at the start we had 14 examples. After splitting on outlook, in the sunny branch, maybe out of those 14 examples, there are maybe 6 examples which are sunny. Maybe there are 4 examples uh, where outlook is overcast, and the remaining 4 is probably rainy. So this is just a hypothetical, I'm saying hypothetically. I'm not referring to the training set that we used before. Okay, so what we do in this step is just transfer the examples in the corresponding branches accordingly. And this is done for each value, that is sunny, overcast, and rain. And then after doing that, we just recurse. How do we do that? We again call the decision tree function by passing in the remaining examples. So for the sunny branch, we pass in the 6 examples here, and we pass in the remaining attributes minus outlook, because we have already split on outlook. So attribute minus best, and the mode of the examples as a default. Okay, so after a subtree returns, right, after a subtree returns, we just add the subtree to that branch. So for example, this is returned. We just add it to this sunny branch with the label sunny as stated in this line. Add a branch to tree with label V and subtree subtree. So this is the summary of the general decision tree algorithm.